The session is being recorded. Of course, we can opt out later on from the recording if you wish. We plan to make the video available after some editing to the public. So just to
Okay,
let you
so
know.
it's good.
Good. So yeah, again, we have originally planned for starting with Mert, but I don't see Mert yet in the call. So maybe we can also start with Rana if that's all right, and then wait for Mert in the meantime.
Yeah, that sounds good. That's fine.
Okay. So let me introduce Mert first. Sorry, Rana first. So the speaker is Rana from University of North Carolina at Chapel Hill. Welcome.
Yeah.
And the talk will be about agents under siege, um, where Rana is examining the adversarial risk in multi-agent LLM systems. Super interesting. So now the stage is yours, and feel free to share your screen if you have any materials to share.
Yeah, I did prepare last minute slides. I can probably share those. Let me
Of
see.
course, yeah.
Uh, do you guys see my screen? Sorry.
Yes, I do.
Okay, perfect. So I believe it's evening over there, so good evening, and it's morning over here, so good afternoon. My name is Rana, and I'm currently a first year PhD student at UNC Chapel Hill. So this was a joint project with some other universities and some other companies as well. And yeah, so in this paper, we just explored the critical security vulnerabilities that arise specifically in multi-agent large language models, considering some kind of realistic constraints. So first, we can actually introduce the problem itself. So most research that's already been done on LLM safety focuses on like single models because you can actually jailbreak them. There's prompt infections, and there's a lot of things you can do. But multi-agent systems where models collaborate introduce like new kinds of risks. There are papers, already existing works that actually tackle this kind of problem as well. But the limitations and the modeling they do in their problems is actually not very realistic in my opinion. So current safety mirrors often don't account for like real world or pragmatic limitations like network bandwidth between agents, delays in message deliveries like latency, and the fact that defenses might only be present on some communication links and not all of them. For example, if you have a topology over here and you would like to jailbreak the model that is like with this whale sign using the llama one, but you don't know like what's on this edge. Some of these edge might be secured by some kind of defense mechanisms, or most of these models would be on different kinds of GPUs as well. So there will be some kind of latency as well. And some of these models might be smaller, some of these models might be larger. So there's also a token bandwidth that needs to be considered whenever they're communicating with each other. So why this kind of problem actually matters? So these multi-agent systems aren't just theoretical, they're actually being used for increasingly complex tasks like large-scale content moderation or coordinating autonomous systems. So if the communication between agents isn't secure, the entire system is actually vulnerable. So the goal is just to design and test an attack specifically tailored for these constrained multi-agent environments. So we wanted to see if we could optimally distribute parts of a harmful prompt across agent network to successfully jailbreak a target agent, even with limited bandwidth and unpredictable message arrival tables while bypassing defense mechanisms. So the core idea is basically instead of sending one large obvious attack prompts, like whenever you do GCG, you have one prompt that you can actually use to jailbreak a model, right? You can actually pass it across your topology and as long as it ends up in the final destination you want it to. So that's obvious. But our core idea is actually to break this attack into smaller chunks. So this chunk could represent the token bandwidth, or it could also account for some kind of latency. So basically, these chunks are strategically like our goal is to strategically send them through the different agents and communication paths in the network. We want to optimize both the path, like the best path that is, as well as we want to optimize these chunks such that whenever the content of the chunks is activated inside some kind of LLM, it achieves the attack itself. So the first major thing we do is actually model the system. we want to see that also each LLM agent itself is a node. Yeah, that's pretty obvious. The connections between them are edges, and crucially, each of those edges have some kind of bandwidth capacity as well as some kind of detection risk. So let's suppose in one of these edges there's a llama guard or some kind of other perplexity guard, for example. Their goal is actually to detect some kind of prompts like these. So that edge will also have some kind of risk of being detected associated with it. So we also quantify it using some kind of we actually quantify it using different models. So we try different models and see what kind of chunks they're able to detect, and we quantify it using that. And similarly, there's also some kind of latency associated with each of those specific specific edges. And finally, we also, so our key components are threefold. The first one is the modeling. The second one is the topological optimization. So in this case, we're finding the best path within this topology that would lead us to a successful attack. So the best path would also have the minimum detection risk, right? We don't want to be detected by the llama guards or whatever the safety mechanisms are. So we want to minimize that, while maximizing the number of tokens we can send in that specific edge. So basically, we actually formulate it as a minimum cost. In this case, cost is the detection risk, and the maximum flow, which is the maximum tokens. So mathematically, if you solve for minimum cost, you actually find the maximum flow, or if you solve for maximum flow, you end up having the minimum cost. There's a cut theorem for that. There's already a lot of existing theorems for those kind of things. So that's our goal, and we formulate this graph optimization as one of those problems and solve for that specific path. And after we have that specific path, there's still some things that we need to consider. Because we're sending in chunks, if we send in chunks, for example, like let's suppose we send a 10 length chunk over here, a 20 length chunk over here, and the whole attack consists of a 30 length prompt. When it gathers over here, because there's latency on each edge, we are not sure if the chunks will arrive in the order we want them to arrive. So they need to be permutation invariant as well. So that's why we actually introduced our loss called permutation invariant evasion loss. So instead of having GCG on one specific prompt, we actually apply GCG on smaller chunks of them. And our goal is that whenever you combine the chunks in any order, you end up having a successful attack. So that's another objective that we add in our optimization. So after we have that, we have our whole optimization flow ready for the jailbreaks. And we can discuss some kind of experimental setup as well. So we tested this approach rigorously. We actually used several LLMs. As you can see, we use different variations of Llama, the older ones and the new ones, as well as the R1 distill versions that are currently that were very popular when we were writing the paper, when the DeepSeek came out. And we also used the Mistral and the Gamma 2 models. There was no Gamma 3 at that time. And furthermore, Gamma 3 is like a multimodal model, so that's that. And we also use 3 different datasets, and all of them are jailbreak datasets. So there is some kind of harmful prompt. We optimize over that specific prompt to get the jailbreak prompt with the goal that it will have some kind of harmful output. They include normally from like political activity to some kind of racism and stuff like that. And for baselines, because this is a very brand new modeling situation, there's not a lot of baselines that we can try. Furthermore, multi-agent systems don't already have a lot of jailbreak advantages, so that's that. And we only have the vanilla prompts, which is like how to do something directly, which will most likely be rejected most of the times, but some models are more prone to actually working on them, and some models are not. While GCG is like we optimize the prompt over, but we only have one prompt. So in our case, we will have chunks, but whenever the chunks are together, it will activate the jailbreak. And we evaluate using the attack success rate, which is the norm. So for our finding number 1, the results were strikingly very good in our settings. So as shown in the table number 1, our method dramatically outperformed the baselines. So we achieved the ASR often to the 70-80 percentages for different data sets, while some of them are harder, while some of them are easier. So there's that. We actually repeated our experiments 5 times for each of those models. So this is because, remember I talked about this topology, right? So how do you generate this topology? This could be random. This could be a full complete graph. This could be a tree, chain, different things. So we actually generate them randomly so that we have a good idea of what it looks like. And because we generate them randomly, we actually run the experiments 5 times each so that we have a good average across all different numbers. And you can see that our method actually outperforms both of the baselines in every single cases. And as expected, vanilla has to be 0, and llama models are stronger when it comes to these kind of jailbreak models. And most of the times GCG is 0 as well. This is because GCG it gets detected most of the time when it comes to different kinds of topologies. Similarly, just to see like whether our attack can actually bypass defenses directly. This is outside the multi-agent setting. We're just directly using an F1 score on a data set. So we have a data set of 100 harmful prompts that are like and 100 non-harmful prompts. So our goal is to actually optimize over those 100 harmful prompts and like get the jailbreaking prompts and see if our different mechanisms are able to detect those or not. So the F1 score is basically trying to see how many false positives and how many false negatives we can get. And we can see that our model has so our kind of prompts are the hardest to detect because they are chunked, and we found out that the smaller the prompt is, the harder it is for these kind of safety mechanisms to detect those prompts. And yeah, that's one of the findings. And lastly, for most of those jailbreaks, the most common strategy is actually to test them across different settings and also see if they're transferable. So by transferable, I mean we actually use the source model, for example, Llama 2, to actually get the jailbreak prompts, and we try them on different kinds of models and see if they are actually transferable to other kinds of models. So the stronger the model is, the better it performs across different models. So that's one of the findings that we have. And another one is that, for example, just like I discussed before, we have different kinds of topologies. So we actually try different topologies like specifically that are most common, which are like chain, tree, complete graph, and random graphs. And we find that if there is only one path to some specific LLM, it's harder for our prompt to actually work. This is mostly because we are actually optimizing over the path as well, right? So if it's a chain, there only exists one path. There is no way we can optimize over it. So we'll always take the most inefficient one. But when it comes to complete graph, we have multiple ways to reach a specific LLM. So that introduces more options for us, and we can actually optimize over it to find the best specific path that will allow us to evade all those safety mechanisms. So that works well in practice. So yeah, in summary, the key takeaways are that we developed and validated an attack strategy that optimizes adversarial prompt distribution across multi-agent networks, specifically considering some pragmatic limitations like bandwidth and latency constraints, and using permutation invariance to handle asynchronous arrivals. If to the best of our knowledge, this is the first time someone has done this kind of thing. And similarly, the key impact is that our work exposes significant vulnerabilities in the current systems, and we don't yet have a good way to do that, but we do know that which kind of topology works well and which kind of topology doesn't work well. Similarly, for possible future directions, I think one of the main one is that we need to test them on some other stronger models, like closed source ones like GPT-4, as well as sometimes there are other topologies that we might not have considered, and maybe some multimodal systems that we can try for the next time. Yeah. So that's more or less on all from my side. Like it's just a summary of the whole paper. So yeah.
Thanks a lot for the great presentation, introduction of your work. Is there any question? So we have 5 minutes for quick questions, and then we move on to the next talk. So
Yeah,
maybe I have. So please go ahead.
Yeah, I was just gonna say, like, feel free to ask any questions.
Oh, okay. So I have one question about the target system. So what is the target system here? The topology of agents. What are they trying to solve? What's the problem they are trying to tackle here?
So we have like a full system of LLMs agents, right? But
Yeah.
let's suppose we don't have access to anything other than this model. But we want to jailbreak a model that is inside this system we don't have access to.
No. My question is, what are these models trying to do, right? So are they, for example, trying to kind of make a reservation at a restaurant, or yeah, I'm
Oh,
just asking of. basic question of what is this model doing? What is the set of models doing here?
So we currently have a very general setting that these models are capable of cooperating with each other to do some kind of thing. It could be anything. It could be performing some kind of action, or it could be solving some kind of reasoning task. So that's something that we don't really care about. That you can use the LLM in any way you would like to use the system itself.
I see. Yeah, of course. But I guess my question is for your evaluation, what kind of tasks did you test?
So we tested on like different jailbreak benchmarks. So if one specific LLM is jailbroken, for example, in a system like this, our ASR is calculated if whether this
Mhm.
LLM is jailbroken or not. After we pass a prompt to the source LLM.
Yes, but okay.
So the target model will output something harmful for some specific prompt.
So why is so I don't exactly know exactly what kind of tasks are there in jailbreaking benchmarks. I guess maybe building bombs or something like that.
Yes, yes, that's one of the most common tasks.
Exactly. So do the agents kind of need to cooperate to solve this task? That's, I guess, my question.
Uh, Actually, no. So normally when in setting when you use like deploy agent,
Uh-huh.
yes, you would like all the agents to cooperate or compete with each other to have some specific answer that is one answer for the whole system.
Okay. Mhm.
But our goal was to like show the idea that if you use one source
I
agent
see.
to attack
Mhm.
another target agent, we can actually do that. So if we are able to do this, we can actually jailbreak another model as well, right? So we can actually jailbreak anything that is inside the whole system so that whenever there's an aggregation point where every LLM has to come up with one specific answer, they can actually output something harmful as a system.
I see. Yeah. Mhm.
Yeah.
Because it also depends on what kind of communication is made between these agents, right?
Yes,
So
yes. Also true.
if yeah, if in this example, like building a bomb, if there's a definite need for the agents to do the communication to solve the task, then maybe there's no easy sort of solution of just letting them not speak to each other, right? I guess
Yeah,
um,
that's true. That's true. But like that would mean that the source agent would need to tell everyone else, right? So it will need to tell everyone else that there's no need to communicate. I will just output every.
oh yeah, okay, makes sense. Yeah.
I
Hmm.
think like one of the main problems in multi-agent systems currently, that what I have from reading different literature as well, is that they don't really have a good way of representing the whole system. Like there is no unified way of telling you like
No. Yeah.
what kind of system it is. Is it cooperating? Is it competing? Which one is better? Which one is not better? Like there is no good way to do that.
Yeah. Hmm.
So like any paper you will read, they will have a different kind of formulation for the system.
Yeah, I mean, there seems to be kind of an appearing like emergent kind of standardization in terms of orchestration layer, for example, right? So there's a planner who's doing all the reasoning and planning, and then kind of assigning the task to different agents. So would that be
Right.
kind of potential kind of standardization of the topology, potentially?
But I still don't think that's that's like the only way that people represent the system, right?
Hmm. Okay,
Yeah.
yeah, makes sense. Yeah, thanks for the brief discussion. That was very illustrating as well.
Yeah.
And let me also, yeah, welcome Matt. Thanks for coming. And so Mert is from Berkeley, and the work that he's going to present is why do multi-agent LLM systems fail? So welcome, Mert, to the Research Trend Connect, and I wish to kind of have you introduce the work that you have done.
Hello. Thanks a lot for inviting us here. I'm today with my co-professor Melissa. We're in Berkeley. I'm a PhD student at UC Berkeley. I hope you enjoy our talk.
Yeah, thank you so much for having us.
Thank you for coming.
So we also have a brief slide deck. Share it. And great. You can't see the screen, right?
Yeah.
Perfect. So yes, this is a work about why do multi-agent systems fail. And first, we should define what is an LLM agent before we like go in and analyze what multi-agent LLMs are, right? And when we have an LLM agent, what we really want is that it should have a base large language model. But when you think about it, what is a language model after all? It is simply a statistical machine that predicts the next token given the context. So to turn this into an agent, it should actually have some agency in the sense that it should take some actions. It should be enveloped, warped in a system, wrapped in a system, which allows this next token prediction machine that we call large language model to take actions, like writing codes, browsing internet, executing tasks. Also, just like you said, LLMs essentially predict, let's say, next actions, next tokens based on context, which brings the issue of prompts, and every LLM agent is heavily influenced by prompts. Of course, the other big influencer being its parameters, but they are learned at training time, and we do nothing with them during inference time. And what are multi-agent LLM systems? A multi-agent system exhibit collective intelligence from agent-agent interactions. So it is not that there's a single agent that has autonomy to make decisions, that is able to use external tools like browsing internet, using calculator to make complex calculations, but also through inter-agent communication, they can solve some tasks cooperatively. And why would we even use multi-agent LLMs? Because most of these large language models are really very large, and they're costly to have API calls. However, there are very good reasons why you would need system where you compose multiple of them. The first thing is you can decompose complex tasks into smaller singular parts that can be tackled easily. Also, if you have multiple agents, you can have a network. You can have a distributed system for parallelism, and also having multiple agents allows you to prompt these agents in multiple different ways, so that it works as a context management system. And also, you essentially have an ensemble of specialized models. Also, a multi-system can be used as a simulation tool for interacting how different conversations turn out. And last but not least, there's a vision that in the near future, everybody will have, as smaller language models get better and better, everybody will start having their own small LLM on their edge device, and these models can talk with each other to preserve security and context isolation. However, even though there are so many good reasons of why to use multi-agent systems, we find out that the most popular multi-agent systems today lack performance, and there's not that wide of an adoption of these systems. And to find an answer to why do these multi-agent systems fail, we propose this taxonomy. When we say a taxonomy, what we really mean is that we identify 14 different failure modes 14 different reasons of how these multi-agent systems fail, along with their definitions. And we group these 14 different failure modes under 3 categories, which are specification issues, intelligent misalignment, and task verification. We will talk them in more detail in the next slides. But first, let's discuss how do you even come up with a taxonomy. So the first step to coming up with a taxonomy is collecting the traces and identifying the failures of those traces. Now, you might ask, what's a trace? Trace is basically the system log of a multi-agent system. So this trace for each multi-agent system consists of agent-to-agent interaction, because agents interact with each other through natural language. They tell each other what to do. And their agent-to-environment interaction. For example, if the agents are writing code, the piece of code they're written. These are traces. And then we manually read these traces to identify the failures. And then we come up with an initial, so yes, in this first, after collecting these traces, we identify failure patterns. And in order to do that, we use some principles from grounded theory, which is actually we borrow or we are inspired to use grounded theory from our social sciences to conduct how these taxonomies should be built in the first place. And after identifying the failures, we essentially come up with an initial version of the taxonomy, and then it comes to how can we make sure that the taxonomy is valid, it is robust, and it is clean. And this brings us to developing this brings us to conducting interrogator agreement studies. Now, interrogator agreement studies are important because if we have a taxonomy which we claim to tell you the failure modes in a multi-agent system, what should happen is that, for example, if I read a trace and if Melissa reads a trace, and if both of us annotate that trace using the same taxonomy, we should arrive to the same conclusions. And interrogator agreement studies essentially is a way to conduct, to make sure that the property that I just mentioned about clarity and non-ambiguity of the taxonomy holds. In particular, what happens is that we sample for 5 traces, and then using the initial taxonomy, we arrived at the end of step 2. We annotate 5 traces, and then different annotators compare their annotations, and then try to figure out where they disagree, and then revise taxonomy until they agree on those 5 traces. And then they sample another set of 5 traces, and then annotate them based on the taxonomy, and then revise the taxonomy. And then another set of 5 traces until a good agreement is achieved. And we characterize good agreements like quantitatively by using a metric called Cohen's kappa score, which is a statistic for interrogator reliability. Also, another thing is that okay, so at the end of these interrogator agreement studies, we arrive to a very good taxonomy that exhibits clarity and non-ambiguity. However, we also think it would be really cool to have automated failure detection, in the sense that if you have a multi-agent system, you can run it and get a trace. And then using our taxonomy, can we build an automated pipeline to tell you what the problems are in your multi-agents? To do that, we develop an LLM as a judge system and validate it again through interrogator agreement studies. And this is the final taxonomy that we arrive at. Now let's dive deeper. And as I said, there are three major failure categories. First is specification failures. The second is inter-agent misalignment, and the third is task verification. Now, what is specification issues? Specification issues are really it's a category concerning the failure modes, such as disobeying role specifications, disobeying task specifications, step repetition, conversation loss, and agents unaware of termination conditions. And these modes relate to poor specification because of errors in system design. And these failure modes essentially arise during the pre-execution stages or early execution. So, for example, in a multi-agent system, you might have different agents with different roles. For example, there's a CEO agent and a CPO agent. CEO agent is supposed to break down the task, and then CPO agent is supposed to make sure the product is good for the task. However, sometimes what happens is CPO agent acts like a CEO agent in the sense that when the CEO agent tells, okay, once we agree, we should terminate, and like CEO actually wants to terminate the discussion because it is a superior officer, but CPO agent just decides to terminate the conversation. So it doesn't obey to its role specifications, which is a fundamental issue in multi-agent systems. Another thing is called inter-agent misalignment. This kind of the failure modes in this category essentially arise during execution stages when agents communicate with each other and there are problems with that. For example, conversation reset, failure to ask for clarification. This is like a failure to ask for clarification among agents, and task derailment, information withholding, ignoring other agents' input, and reasoning action mismatch. So ignoring other agents' input is crucial one. For example, the one on this slide. What happens is that this is taken from April environment where you have a supervised AI agent, and the supervised AI agent tells, okay, log in with username and like it's an email address and a password. However, the Python agent insists on using phone number and doesn't really consider what the supervised agent tells, resulting in a failure of the system. Another thing is task verification. Task verification essentially arises in premature termination. Arise at the end post-execution stages of multi-agent system trace. And the main modes we identify are premature termination. That is to say, when a multi-agent system ends early, or there can be a verifier that's supposed to make sure that the system is behaving correctly. However, that verifier might be incorrect verification, or there are cases where there is no verifier at all. So, for example, an example of a bad verifier or a useless verifier is illustrated here. Here, the user wants a chess game with inputs like the formal chess notation. For example, QF7 means queen goes to tile F7. However, the AI agent designs a game. The software agent in this multi-agent system designs a game where it accepts inputs in the form of x1, y1, x2, y2, which are the input and output coordinates in this Cartesian system. And the verifier looks at the game, checks that the game runs, and says, okay, it looks good. However, this is not what the user wanted. The user wants to input formal chess notation, not this kind of notation. So yeah, this is another category. And you might say that, okay, some of the failure categories are related, and that's perfectly true. For example, like here, the verifier being weak resulted in also disobeying task specifications, which was a failure mode we listed under pre-execution stage of specification issues. And indeed that when we look at the heat map, analyzing the correlation of different failure modes and failure categories, there exist patterns. However, we arrived to the conclusion that all the failure modes are necessary because there are no super strong correlations across categories or failure modes that are like more than 70%. But indeed, it is interesting to analyze how different failure modes can co-occur. Now, okay, given that we have a taxonomy, why does it matter? How is this taxonomy ever useful? And one answer to that is that failure, given a multi-agent system and its traces, you can use our taxonomy essentially as a debugging tool to understand what went wrong with your system. Because let's say you have a multi-agent system with which you are unhappy and you want to make it better, but it is really non-trivial to know what went wrong or what kind of, like, you know that the tasks fail, but you don't know how the tasks fail and or why the tasks fail. In fact, this is the title, this is the main, let's say, angle of this paper. Like we give a standardized breakdown of why do multi-systems fail. So based on that, based on the competitive modes, we also list some tactical approaches and structured strategies. And tactical approaches are things like improving the topology, network topology of your multi-agent system, or improving the prompts to the agents, which are tactical. So based on the task at hand, you should think about what to do. But structural strategies are more comprehensive changes, like, for example, having better units or standardized communication protocols. And in our paper, since the main focus is developing the taxonomy, we only did a few tactical approaches to see if math can be applied. And indeed, we see that. So the left-hand side, it's on AG2 multi-agent system, and the right is on ChatLab. We first apply prompt interventions, so that is to say, changing the prompts, and then we apply topology interventions to both systems. And indeed, we see that our taxonomy is able to categorize the degrees and failure modes that's occurring after these interventions, showcasing its ability to be used as a development tool. So in conclusion, so even though the title might seem a little pessimistic, we are definitely hopeful about multi-agent systems in the future. However, in order to make them better, we note that system design is very crucial, and verification has paramount importance. And MAST, which is a taxonomy we presented in the paper, is the first multi-agent taxonomy out there. And we really offer it as a practical tool for developers. And we also have a guideline for how to build more reliable and effective multi-agent systems. And thanks a lot for listening. We open sourced our code and data set on GitHub. Please feel free to check it out. And the paper is also on archive. We submitted a newer version yesterday, so it should be online either tonight or tomorrow. So yeah, please be tuned.
Thanks a lot for the presentation. So maybe we don't have much time, 50 minutes for discussion, so we can jump directly into potential discussion. So Any question to anyone? So maybe for the second, for Mert and Melissa, I have some questions. So it sounds like it's a great talk, and it really tells the shows the reality of potential use of multi-agent systems. Is there, so I've only seen kind of negative example here where multi-agent systems are kind of failing. Is there any success cases of multi-agent system as well?
Yeah, so like during our study, when we are looking at different multi-agent systems, there are definitely cases where the system result interests us. Like for example, if we go back to the like the initial plot that shows the success rate versus failure rate, we are focusing on the failure cases because we want to make it better. But if you look at the other side, there are also success cases, right? So it doesn't mean that multi-agent system doesn't work at all, but rather we could make it better for it to be like reliable and then for it to have more like wild adoption. So one example that I can give was like I was profiling Menace, Open Menace. And okay, we don't have that number up there yet, but basically it was able to like interact with the browsers and then it will be able to generate pretty good results. I think like a concrete one that I was working with is that I was trying to ask it to build a website based on the code that I have as a server, and then it was actually able to do that. So I think that was like one example.
Okay, but the example that you just brought up is more like agentic system as opposed to multi-agent system. Is that right? Or did you also benefit from having multiple agents solving the task?
Oh, that is a very good point. So there is like Menace and then versus Open Menace. In Open Menace, they do have a repos, like they do have an option to run it as multi-agent system. So we have also like test like the with multi-agent system and seen like good cases as well.
Okay. So intuitively, you're mentioning in one of the slides the conceptual benefits of having multiple agents, right? Like for example, it enables you also from computational reasons, right? You want to save time for doing this, right? And you can basically distribute the task to different people, different agents here. Are these examples that you mentioned, are these kind of in some product already, or are these more like at the lab level?
So yes, like we know that some of them are commercially exploited. For example, some companies that reached to us mentioned that they for to produce some agentic systems in real life, they use a multi-agent system with even 40 to 50 agents, essentially as a way to decompose tasks and to manage context, so that a single agent might get confused on what to do on a complicated query. However, when you have, for example, 40 agents, each of the agents are tasked with a very specific thing. Apparently, they have a reliable system. And another success, like, for example, in AG2, which has, for example, multiple agents discussing a math problem, we use GPT-4o here. And the single agent success rate of GPT-4o is about 40% or 45%. With AG2, like the LLM behind it is GPT-4o. But the system's success rate jumps to almost 60% or 45%. So that's another success rate of this collective intelligence. Like, yeah, different agents talking with each other, different contexts, etc. But of course, like, why is it not 100%? Or can we push further?
So in a sense, your work is kind of trying to kind of remove the roadblock against attaining the last miles of the improvement due to multi-agent systems. Is that the right way to kind of understand the work?
So that is true. But we say having done better because like there are success cases of multi-systems, but there are also catastrophic failure cases. So I wouldn't say we are in the last miles of like AGI or having good multi-systems. But yeah, we hope it's useful like along the way.
Yeah, so basically, if we look at the last slide, so like despite the underlying LLM may have its own limitation, whether it's like hallucinations or instruction following, we believe that there are failures that come from the multi-agent system itself, like regarding how it's been built and how it's been designed. And we also show that in our case study that if we improve the system design of multi-agent system, we are able to get improvement while the underlying LLM is still the same. So we hope that they are like sort of complementary, that we can have better multi-agent system, and along like the way having better underlying LLM would also be great as well.
Very interesting. Do we have a better recipe then for kind of building the multi-agent system based on your work?
So the two interventions we did regarding designing the topology again and improving the prompts have some benefits as also captured by our taxonomy. However, for example, actually fine-tuning these models with reinforcement learning or having like better unit test verification for coding tasks are very important research topics on their own right, which we are hopeful it will improve the system. We didn't have like they were a little bit out of scope of this paper, but like we certainly do not think that like these multi-systems can't be improved. Yeah.
Yeah, so basically, as Mert said, like for the scope of our current study, like this study, we try to take a very grounded approach and only discuss like the observable failure patterns that we see. And then we did try to bootstrap and understand what is the underlying root cause, which then we believe could lead to like better building like multi-agent system. And it's actually really difficult to tell what is the underlying root cause, because there could be so many factors that contribute to the failure. So here we list out some of the approach that we think might be helpful, and then we also do case study on it to show some improvement. But these are definitely not enough, and then like that's why we want to have this taxonomy as a guide for research agenda for the entire community, working towards like building better system together.
Definitely, yeah. Thanks a lot. Any other question from anyone else?
Safir, and we just published a paper on a survey paper on evaluation of agent. So my question is from that point of view. So based on your work, great presentation, by the way, both Mert and Melissa, it interests me to know what kind of feedback your work have on how to conduct a proper evaluation of agent to make those kind of conclusion more native to the benchmark, because a lot of the benchmark are focused on success rate and not all the more fine-grained dimension of the success and failure point of agent, as your work exemplify that it's very necessary.
Yeah, that's very interesting. I see. So that's a very interesting point, because we really try to focus on why, like, giving a trace, what are the problems with the multi-agent system in that trace, but our goal is slightly different from evaluation or evaluation benchmarks in the sense that given two different multi-agent systems, we do not want to say, or we do not aim to say which one is better or which one is more, I don't know, strong or generalizable or robust. But what we really mean is that, like, yeah, given a single multi-system says, what are inherent problems with it so that we can develop it. But perhaps like a work on top of our work, like a follow-up, could be something along the lines you said, in the sense that given two different multi-agent systems and using their failure modes, can you tell which one is superior to the other on different aspects? It's like I see. It's like if in head-to-head comparisons, you have those maps where, okay, in one area you are better, in one area you are worse. Those kind of comparisons.
Yeah, thank you for the very interesting question. So I guess just to put in simple words, we are trying to help diagnose what are the problem in the multi-agent system, and hopefully it will be a useful information for people to make it better. So it's another dimensions in evaluation.
Yeah, I'm completely understand that. The question was more around about how to utilize that, to build such benchmark that alleviate the need for doing more error analysis, that is finding those kind of failure point, but make them as kind of the feedback of the benchmark itself. Because a lot of benchmark is not just give you the outcome of the ranking of the model. So a lot of benchmark can also give more fine-grained kind of feedback. What kind of quality are actually the model succeed and where it's fail, and in that sense it's have some connection to what you discuss here. So more as a follow-up, or as like, what are the takeaways that relevant to those to the evaluation domain?
Yeah, that's a very good point. Like in my personal take, to build a good benchmark, you should be able to differentiate between systems. So knowing that these dimensions or these failure exist, people can build benchmark along these lines to be like to differentiate between the system. So that's a very interesting thought. Thank you.
Yeah, thanks.
Any further questions? So I also have some to go back to the first talk, right, from Rana. So this is very interesting, and we also thought about potential kind of issues with propagation of errors or propagation of attacks within some topology of agents. But I was kind of, we were kind of touching upon both of the topics of today, actually, because we were thinking about that, and then we realized we don't know much about the exact kind of standardization or exact kind of use cases of multi-agent systems. So we're not so sure about the exact target model that's going to be potentially useful in practice. So, or applicable in practice, because I can also imagine that depending on the target model, right, the attack could be more successful or more less successful, right? So I'm also wondering, like, the results that you get from this benchmark, saying, yeah, this topology is kind of susceptible to this kind of attack and so on. How do you think do you think this is kind of this is something that could be relevant in the future as well, or do you think the design of this benchmark should be kind of changed in the future depending on the kind of the usual practice people follow in multi-agent system design?
Wait, so this question is from Mert, right?
For you, Rana.
Oh, okay.
Yeah.
So, wait, can you repeat your question?
Yeah, so I can repeat quickly. So, do you think the target system is the target we are kind of assuming is quite important for evaluating the success rate of the attacks and so on, right? If the target is kind of supposed to be vulnerable, right, in the first place, then the attack will be kind of successful against these kind of targets, but it doesn't really imply that the actual systems will likewise be vulnerable, right? So it's very important to align the target that you're assuming in the attack benchmark and the actual kind of models that we see in the field.
Right.
Can you comment on like how realistic these targets will be?
So in our paper, we only care about jailbreaking one specific model, right? So that doesn't really mean that the whole multi-agent system itself is jailbroken. That's true. I agree with that part. But the thing is, like, in my opinion, if you can jailbreak one model in the system itself, you can actually try to jailbreak every single thing in the whole system. But if that's possible, then you can actually jailbreak the whole system, right? So that's one of the goals that we had for our paper, just to showcase the key idea that we can actually jailbreak one model instead the whole system. And if we are able to do that, we can actually port it to jailbreak the whole model itself. And I think it really depends on what kind of models they are. As you saw from some of the results we had for the transferability, for example, if the jailbroken model itself is very hard to jailbreak, for example, if it's a llama kind of model, which are normally very safety aligned, they're harder to jailbreak than, for example, Mistral and Gamma. So if you actually are able to generate prompts using llama, they work very well on Mistral and Gamma. But if you are able to generate prompts using Mistral or Gamma and you apply them to Llama, it doesn't work very well. So the transferability has some kind of effect depending on what kind of model you're using. So I think like going forward, if it depends a lot, like what kind of models you're using as well. So if you're using open source models, it's very easy to evaluate using different benchmarks, what kind of models are easy to jailbreak. But if you're using closed source models, I think it's very hard to see which kind of model would be the best to use in these kind of situations.
Yeah, thanks for the answer. And now we are kind of at the time where we have to close the session officially, but feel free to do further discussion if you wish. I'm going to stay for a few more minutes, but let's officially close the session now. I'm sharing the link to the feedback because we are kind of in the first iterations of this Research Trend Connect session. Your feedback is very important. Tell us how to serve you better in the future. Okay, so please use the link to give us feedback. And I'd like to thank Rana and Mert and Melissa again for giving a very nice talk and being available for discussion afterwards. Thanks again.
No worries. Thank you so much for having us.
Yeah.
Also, in the next phase of our work, we want to basically make our taxonomy and our LLM as a judge available for the general public, so that people can update their traces. So, like, if you have a multi-agent system, and if you want to see how it performs in our mode taxonomy, it would be great to like get your feedback and.
And also our second version of the paper will be available soon, so stay tuned. And we hope that you guys can check it out and let us know if you have any feedback as well on our end.
Thanks a lot for that. The session is recorded, by the way, so we'll try to make this available in some formats. I'm thinking of YouTube now, but after some editing, you can opt out if you wish later on. Just tell us. But yeah, otherwise we understand that you have agreed to being recorded. So we'll go ahead and post this at some point. Just to let you know.
Right, sounds good.
Thanks.
Thank you.
Yep, thanks a lot. See you again. Keep in touch.